Hey, this is Amber, and today we are going through matrices, and it's really exciting, so hold on. We are going to have a lot of fun today. So the first thing that we do is we do a little bit of a warm-up game, a little bit of a math game to get the kids' brains working and get them thinking about things. And so the theme, hold on. Okay, I had to move a trash can out of my way. Okay, so the theme is still quick flip arithmetic. And this week I'm still focusing, a few weeks ago we talked about the distributive property. Hopefully, yeah, I think that shows up a little bit better for you guys, this marker color. Okay, so as a reminder, distributive property is A times the quantity of B plus C is the same as saying A times B plus A times C. And they've been kind of memorizing this since foundation days, right? But it's good to just write it up there so that they have an example. They make sure that they know how they're plugging in stuff. And then the next thing we do is flip from a card deck. And so when I flip, I have a 2, which will be my A term. I have a 4, which will be my B term. And I have a 3, which will be my C term. Okay, so I will set that aside. And you may have heard on my last few videos, I plant the first few cards because I want to make sure the first example is going to work out nicely and I can quickly calculate it and the kids can see how it works. So I always plant those first few cards. Okay, so they can write this out and they can say this is A, B plus C. And I have some kids that'll say, can't we just add what's in the parentheses? Sure, you can, totally. So then that's 2 and 4 plus 3 adds up to 7. So 2 times 7 is 14. If you want to write it out a little bit longer, you could show it in this format where you do 2, where you're doing this. You distribute the A with the B, so 2 times 4, and then you add A times C, the 2 times the 3. And so you have 8 plus 6, and you still get to the answer of 14. And one of the Challenge A directors had a great idea, which is I have dry erase boards for my kids. We use them for roaming around the empire, or around the empire in Latin when we play that. So I'll give them all a dry erase board, and I'll give them the first 3 cards and let them try to calculate this in whatever way they want to solve the answer. And so hopefully they get to 14. And then I'll write it up on the board because I always want them to see how we solved it in case I have a kiddo who doesn't quite understand. They're probably not going to say, I don't understand. So I think it's nice to just put it up there so that they can see it. If you want to make this a little bit more difficult, so for your kiddos that can easily calculate through this, Dr. Gilpin recommended turning it into a fraction. And so in order to do that, I'm going to find a denominator. I'm going to turn these each into a fraction, and I'm just going to grab another card to get a denominator. So in this case, I have 6. So that's going to make each of these into a fraction. Okay, so if we have that listed out as the fraction, then we have 2/6 times 4/6 plus 3/6. And so you'll have kiddos that say, let's just add those together. So you have your 7/6, and then you get 14 over 36. And those can both be divided by 2 to simplify it. And so you end up with 7/18. If they want to branch it out and write it out kind of the longer way, that also still works. So you have 2/6 times 4/6 plus 2/6 times 3/6, and 2 times 4 is 8 over 36. 2 times 3 is 6 over 36. And then you add those together, you get the 14 over 36, and they still are divisible by 2. So you can simplify to 7/18. So there you go, 2 ways to do distributive property. One is maybe the more simple way, just so they can master the concept of distributive property. And a second is adding some fractions for the kids that want a little bit more of a challenge. And my guess is with 5 minutes, I only have time to do those 2 examples and we're probably able to move on. So let's move on. Okay, So we are in matrices. The first thing that I do is I have my kids turn to the math map page and I say, where are we? And they will probably notice we are still in complex, but yay, we have made it to the fourth dimension. So matrices is the first part of our fourth dimension discussion. And so we're in the fourth dimension, exciting. What does that mean? Anybody have an idea of what fourth dimension means? And I'll give them a moment to see if anybody says anything. Pretty much it's intersecting spaces is kind of the really short definition to it. But it'll be exciting to see what they have to say and what they come up with. And specifically, matrices are letting us organize information. That's kind of a quick idea of it. So we say, for our exordium, let's look at the cover. What do you see? What does this look like? And so they might see how there's many smaller boxes and it makes up a whole, a bigger part. If they don't know, you can point out that this is a photograph, so this is an actual place. And then I would ask them, I'll tell them, I've actually been to this building because we lived in Milwaukee for years. So I've been to this building and I've seen this view. Can you think of how I was standing or positioned in the room to look at this view? And they might say, well, are you looking out the window? That's a good guess. And I'd say, this is actually looking up at the ceiling. So this is the ceiling view of that building. And something that's really fun is what that building looks like actually on the outside of the building. So if they haven't seen it before, that is the Milwaukee Art Museum. And that is what it looks like. So there you have Lake Michigan off in the background. And that wingspan is a 217-foot building part that actually is movable. So in the evening, at night, those wings close up. And it's kind of like the bird is sleeping on Lake Michigan. And then in the morning, the wingspan opens up again, like you see in that picture, and it's open like a bird soaring over the waters of Lake Michigan. So I just think that's really cool, and I wanted to point that out for the kids because it's cool to see. But the thing that they should be seeing is that we kind of have this organization of smaller boxes into a bigger system, and that's the way to think of a matrix. Matrix actually in the Latin means womb, and I'm not trying to see the relation to womb per se, but if you think about like baby bees growing in a nursery, right? They're going to be in honeycombs and they're going to be placed, that larvae is going to be placed throughout the little honeycomb apparatus. So it's kind of a way to organize things. Matrices are kind of like the graphs we had last week in populations too. So they help us visually organize our information and see it and then work with it a little bit easier. The next thing I would do is read the quote, and it's kind of talking about how God mentioned the mind of God and this elaborate, complex system that comes together. And so one of the things to point out, and it mentions this in the conversations, is that God gave his word through the Bible. And so the Bible for us is kind of like this matrix of books and chapters and verses and things in a 3D world for us so that our simple 3D minds could try to understand God and his vastness. God also sent a 3D person. He sends his son Jesus to come and be in our 3D world with us to help us understand him, because we are still just simple 3D beings, human beings, and it's hard for us to understand other dimensions. And then I would ask if they have any other comments about matrices. Then the next page we go into is the invention page. So after our exordium, the next thing we go to is our I2 or our invention page. And what I think I'm going to start with is tell me what you know about 4D and hyperspace. And maybe they will notice that they have a definition of hyperspace at the top here. And they can read that it says hyperspace is that which has infinite length, width, height, and breadth. Okay? And another way to maybe think about that is time. So length, width, height, and time. But I love the concept of breadth as being that fourth dimension. And I love that Math Map uses that. In Ephesians let's see, verses 17 through 19. So this is in the King James Version. It's a little bit different in some other versions, but it says, that Christ may dwell in your hearts by faith, that ye, being rooted and grounded in love, may be able to comprehend with all saints what is the breadth and length and depth and height, and to know the love of Christ, which passeth knowledge, that ye might be filled with all the fullness of God. And so I love the concept of fourth dimension's not just time, it's this breadth, because it almost calls to like a bigger spiritual component, which as Christians, we know there's that bigger component. And so just limiting it to a definition of time doesn't really seem like it's fully gathering everything that's kind of beyond our understanding of three dimension. Okay, so they use breadth as that fourth part. It does, though, however, make it a little bit easier in giving examples if we just talk about time. So I'm going to kind of like bring down breadth to just be the concept of time and give a little bit of an example. So if I told the kids, if I told you, meet me tomorrow at Starbucks, would you be able to do that? Did I give you enough information? Well, I told you you're meeting me, and here's me, and this is the earth. I'm on the earth, and this is my radius. So my distance from the center of the sphere of earth is 1 point of location. So I have my 1 point here, 1 point of location, which is my radius. How about another point of location? If I just said Starbucks, meet me at Starbucks tomorrow, which Starbucks? There's millions of Starbucks, hundreds of Starbucks at least. Which Starbucks am I supposed to meet you at? I need two defining points. I need a latitude and a longitude, latitude and longitude. Because you can assume I'm on the Earth's surface. That's one of my points. But I also need a point here for latitude, and I need a point here for longitude. That tells me the other point. So now I have me on the earth, and I know the location because I have a latitude and longitude. But am I expecting you to go to Starbucks and wait all day tomorrow, and then at some point I'm just going to show up? Probably not. I'm going to have to give you a time that we're supposed to be meeting, because I want my path of the whole day to cross with your path at the same time. So I need to give you a time. And that time becomes that fourth dimensional space, that fourth part. Okay, so that's one way to think about four dimension. Another thing to think about is how time for us as a 3D person is linear, right? So and it's constantly in the present. I am constantly in the present, and I'm going to keep going forward. I can't go back into the past, and I can't jump ahead into the future because I am limited in my three-dimensional space. Just like if I drew a picture, this is my little 2D bean, my 2D thing that is flat on this plane. A 2D item can be bounded by a 2D shape. And we have talked about a square being a two-dimensional shape. So there's my flat plane person bounded by this 2D shape, can't go anywhere, can't move off. Me as a 3D person, I have to be bounded by a cube. So here's me. And I'm in a jail cell. Okay? Kids will get a kick out of this. Okay. So if you want to trap me, a 3D being, you have to put me in a 3D shape, bounded 3D shape. And so that is going to be a cube, or the jail cell, okay? So that's 3D. To a fourth dimensional being, the fourth dimensional being would come in and say, well, just go to a time before you were put in the jail cell, or go to a time after you've been released from the jail cell. Just go to a different time, and that's how you are no longer trapped by that cell. And I would say, I can't do that. I don't know how to do that. I can't move through time. But to a fourth dimensional being, that time is flexible. They can do that. We can't do that, but they can do that. Okay. So one of the ways they show this they actually kind of show two 4D representation, but of course they're drawing this on a 2D plane. They're trying to give us this view of like three-dimensional and then trying to explain it through time. That's a really hard thing for them to do. I give them high props for trying to do that. Let me see if I can kind of explain it. So the top example, a space moved through time. So that's more the idea of what that fourth dimensional being is saying. Just go to a different space, go to that different time when you were out of the jail cell. And that's kind of the space, that infinite length, width, height, breadth, being able to move through that time. And so that's the first example. And what this reminds me of, you might ask the kids if they've read A Wrinkle in Time. That was one of my favorite books in grade school. And it was so futuristic and science fiction, and I had no clue that tesseracts were like this real concept and this real thing, that we have theories of it, but it's pretty well respected that there probably is this ability for something to be able to do this, just not necessarily us. So a tesseract is kind of what you're looking at with that idea of being able to move from one time to another. And the other example I had is like if I wanted to travel to the moon, I'm limited by how long it would take me in a rocket with how fast I can travel and get to the moon. But if you had a tesseract, you're changing that time difference. So you're being able to do something at a much quicker time. And part of that probably involves speed. And we'll talk about that more in a minute. Okay, so that's maybe the first example. The other thing that they're showing here is the intersection of the spaces. And so this is maybe more, the way I see it, is more the concept of being able to access all those times at all given times. And they actually show an example of this in the movie Interstellar. And so if you have any kids who have seen that movie, maybe they remember how there's at this one point, he's almost kind of seeing the same scene or the same moment in time, but he's kind of seeing it from different viewpoints, or he's accessing that time in a bunch of other times. And so it's not limited by this linear time, which we as a 3D person is limited by. Okay, so hopefully I haven't lost you yet. Let's look at this like geographically with an image and see how this kind of relates. So 0D, 1D, 2D, 3D, and 4D. And my 4D drawing is going to be really bad, I can already tell you. Okay, so 0 dimension. We have our point, right? And our point has no length, no width, no height, just a point. In 1D, we can have a line, and that is unbounded. If I want to have a bounded, closed shape in 1 dimension, I have to put some endpoints on it, and I have a line segment. So now I have it, and it is bounded by 2 points, by 2 0-dimension components. So it's bounded by 2 of those 0-dimension components, the points of a 0 dimension. If I move up into 2D, let's get our square back, because we were talking about a square. And the square is on my flat plane. If I have it bounded, so the square is a bounded shape, it is bounded by 4 line segments. So this one is bounded by 4 one-dimensional shapes, 1D components. If I go up to 3D, I have my cube. And there, if you look at the planes, the different planes or the sides, there's 6 of them, right? So it is bounded by 6 of the 2D shapes, those 2D planes. And if we get up to 4D, and I don't have a great way to draw this, I kind of have one in my lesson plan. You can try to make an attempt to draw kind of multiple cubes onto each other. And what you end up seeing is that it is bounded. I also found a video on this, so I might actually show them a quick little video what this looks like. But it's bounded by 8 3D cubes. So it's kind of like if you have 8 3D cubes, but they can almost like interact into each other and move within each other. They don't have as much of a limitation as like our 3D solid item would have. Okay, so each new dimension is bounded by 2 more items of the previous dimension. And so that's kind of what I want to show you here is you can think of it that way. Maybe it's an easier way to think of it. So infinite would keep going. Finite has an end or allows you to bound the item. And when you bring up those bounded pieces onto the next dimension, you're going to make your new shape based on other bounded pieces from the last dimension. Okay? That's pretty much my definition, circumstance kind of relationship stuff and explaining what you're seeing on that invention page, but hopefully laying it out in just a quick, simple way so the kids can understand it. Now we move on to memoria and arrangement, which more so focuses on actual matrices versus I would say the invention page focus more on like the concept of 4-dimension. So let's talk about a little bit on the grammar of matrices. My guess is none of the kids will have seen this before. I don't remember seeing this, and I went through calculus and college math and graduate math, but I don't remember seeing these, so maybe I didn't, I just don't remember them. Who knows? They were around. They've been around for like a couple hundred years, so they were even around when I was in high school, but I don't remember. Okay, so the first thing to do is just show a matrix. So a matrix kind of like has this partial box thing around it. And in this case, I'm going to put some numbers here. And this is what I laid out in my lesson plan. So that's where I'm getting these numbers from. Okay, so when you are looking at a matrix, you are looking at the rows, and the rows go across. So rows, and this is row 1, and this is row 2. So rows go across. Wow, that blue marker really doesn't work. And then you have columns. And the columns go down. So this is column 1, column 2, and this one is column 3. Okay, so rows by columns. So I would call this matrix a 2 by 3 matrix. And that's because you always list the rows before you list the columns. Okay, rows by columns. And so maybe I'll even draw another matrix on the board and just say, okay, what are the numbers in the row, in that first row? What are the numbers in the second row? What's the numbers in the first column, second column? Okay, so that's an example of rows and columns. So that's how they're reading it. And then you can also look at a specific element. So you could say, I care about the element A, and you could write it out like 2, 3, and it's kind of like this little subscript. You don't have to have the comma in there though. It could also just be element A, 2, 3. And the way you're reading that is that 2 is your first part, which is your row, because you're always reading from the rows first. So this is row 2, and then 3, column 3. So if I go to row 2 and I go to column 3, my number is 5. So element A, 2, 3 is equal to 5. Or you could write it out like this, equal to 5. And you could ask another one. You could say, what's element 1, 3? That would be -4. What's element 2, 1? That would be 6, okay? So that's how they're reading the matrix. Easy, huh? Totally, they got this down. And then the next thing that it talks about on the page, on the arrangement page, is adding together matrices. And the thing to know about adding or subtracting matrices is that they have to be the same size in order to add or subtract them. So they give an example in the book, and I might just write this on the board so that they can see it and they don't get overwhelmed by all the other information that is on that page. Okay, and then we're just adding them straight across. right? So 2 plus a negative 2 gets you to 0. 3 plus 3 is 6. 4 plus 4 is 8. And 5 plus 1 is 6. So there you go. That is just adding together. It would be, if you had subtracting, you're just subtracting. This is math that they already totally know how to do. It shouldn't be hard. They've done a lot of this stuff, and they'll have examples like this on their student pages that they work through. Now, multiplying is a little bit harder, and I don't remember if the student pages has them do any multiplication. If they do, it's pretty simple. But multiplication, so let's take the matrix 2, 5, 3, 4 on here. Okay, so if I want to say 4a, so I'm multiplying 4a for the matrix. So this is the same as saying, well, here, I'll write it out in longhand, and then we'll show what it solves to. 4 times 3, and then 4 times 4. Okay, so all you're doing is you're multiplying 4 into each of those elements of the matrix A. And so then if I solve for those, I end up with 8, 12, 20, 16. So there you go. So multiplying, you're just multiplying it out like that. A quick little thing to note, if it's not just the number multiplying by the matrices, if you want to multiply like one matrix and another matrix, you can do that. But the columns of the first matrix has to match the rows of the next matrix. So I could multiply a 2 by 3 matrix with a 3 by 7 matrix. It doesn't matter what that number is. What matters is that the column of one matrix has to match the row of the other matrix in order for you to be able to multiply them together. So those are the two rules. For adding and subtracting, they have to be the same size. For multiplying, the inner amount, so the rows of one column, or rows of one matrix has to match the columns of the other. Okay. The last thing that they talk about on this page that might be useful for them to kind of look at or pay attention to is the determinant. And they're not using determinants yet, probably not using matrices a whole lot yet either. But you care about the determinant because it is useful later when you're trying to get the inverse of the matrix, or there's certain linear equations or things in calculus that they're going to come to, and they need to know the determinant. So this is just something that you can solve for in a matrix, and they can totally learn how to do it now, and then they kind of have some understanding of what it is. So when I say determinant, like the determinant for matrix A, I would write that determinant of A, or the other way you could write this, the other grammar for this, is that you have these two solid lines around A, not to be confused with absolute value. Okay, this is for determinant. And the way to solve the determinant, so let's say determinant A, or A, is where you would take here's my matrix, and what you do is you take your first two and multiply them together, so you have A times D, and then that is positive, but these two come together and they are negative, so I'm just going to minus B times C, and that's it. So you're taking those two numbers together, multiply them, minus these two numbers that were multiplied together. And whatever you solve, that number is your determinant. And so they don't totally need to understand what determinant means, but knowing how to solve that in a simple 2 by 2 matrix, that's all they need to do for now. It can be solved in other matrices too, but just the 2 by 2, that's the only one they have examples of on their papers or in their student pages. So if I wanted to do an example, I put an example in my lesson plan. And so we would have the determinant is 1 times 4 minus, put the parentheses around this so it's easier to read, 2 times 3. Okay, so we have 4 minus 6 which is -2. So the determinant equals -2. Okay, so that was the other major thing on that Memoria page. Now, in terms of the graphs, they kind of go through more examples. They show you a lot of stuff tied to matrix. I think the main thing that I wanted them to understand is that 4D is impossible for us to experience. This is bigger and greater than we are as 3D beings. But we can start to recognize these patterns or understand that things are possible. It's just something that we don't have knowledge of yet. We can't fully grasp it because we can't live in it. But the matrix, a perfect point of a matrix, is to organize things in rows and columns to make it easier to solve things. So my sister is a junior at an engineering school, and I asked her, do you actually use these matrices? And she said, yeah, all the time in solid mechanics, which is the whole concept of like they're building a rocket and it's going to get really hot and be under pressure and heat, and how much is it going to melt, or how much are those force vectors going to change something else. So she said she can easily have 6 equations running at the same time with 6 different unknowns, and she's using that to solve something. And so the matrix helps her organize those different unknowns for the different equations. And so this is something apparently she uses all the time. So it's important for our students to have some base understanding and see how to get to there. And then for the student pages, the first page, the top of the first page is just a definition. So they're talking about what hyperspace is. And so this, you just pulled back from that invention page. So you can just ask that. And then I think it would probably be helpful to go through some of the elements then of either this page, or you can go on to page 2, but I'm not going to assign 2 kids to do like the whole page. I don't feel like it's fair, and it's a lot for them to handle. So I think instead what I'll do is break it up. So like maybe on a little pair, I'll have them just do like the top 2 bolded items, and then another group does the next 2 bolded items, and then another group does the next 2. Or we could pull from the second page and kind of divide it up like that. That was actually my plan, is to take this second page and have one group solve the first 2, somebody else solve the next 2, and somebody else maybe do this side. And so we're kind of working through a little bit less of the problems together in class, but helping them get an understanding of how this works together. So that's kind of my big goal with matrices. If we don't get to a ton of the student problems, I think they need to kind of see the layout of how they're supposed to solve these problems. And so there might be a little bit more instruction in this week than I normally would give in another week. Because I'm not sure they're just going to like land on it and understand how it works and how it fits together necessarily. So I think this one needs a little bit more, a bigger understanding. So there you go. That's some of the stuff that I have on matrices. I hope it's exciting. I hope you think about all the possibility and what this all means, and how, you know, these other dimensions, this 4th dimension. So we know maybe it has to do with time and movement through time, and there's more dimensions, and there's 5th dimension and 6th dimension, and our little minds and our bodies only work in 3D, but there's something bigger. You know, God is bigger. God has access to all the dimensions, and he brought things into our 3D space so that we could better understand. But as we start to understand how time works and relativity, so this is Einstein's theory, where he talks about how as something's traveling faster, that it's having less time that elapses. So this is the concept that when we are here on Earth, an astronaut who's out in space is actually aging at a lower rate because there's been less time that has passed for them compared to us back here on Earth. And if you could travel even further, that would even more so be exaggerated and a bit even bigger case. And so some of these concepts where, yes, time kind of works linear for us, but as you get closer to the speed of light, you can change how much that time is, what the duration of the time is. Time is not a static, constant thing. That's really cool. So anyway, hopefully they're starting to get excited about some of the stuff that's upper math that maybe they didn't even see till college, that we start to expose them to so they can realize just how big and vast and wonderful God's world is. Okay, thanks so much.